Hello, and welcome to this presentation on the large displacement behaviour of infinitesimal mechanisms using graphic statics. My name is Cameron Millar, and I will be presenting our work on this paper alongside Allan McRobie of the University of Cambridge and Bill Baker of SOM. We hope that you enjoy this video and find the work interesting. We refer you to the paper in the conference proceedings for a full technical discussion of the methods and more examples. Some structures contain mechanisms. These mechanisms are nodal motions which produce no first-order change in member length. States of self-stress exist when bars that can contain axial forces without any external loads. In general, mechanisms are shaky and possess zero stiffness, so are avoided. Pre-stressing the structure so that it contains axial forces can either stabilise or destabilise the mechanism. Such structures are called prestress-stable mechanisms. Finite mechanisms, which contain zero bar extensions, are neutrally stable, but infinitesimal mechanisms, which include second and higher order bar extensions, can be stiffened sufficiently using pre-stress. Tensegrity structures are a class of real-world structures which rely on this effect. These beautiful sculptures by the pioneering artist Kenneth Snelson reside in the lobby of the SOM office in New York. They produce an appearance of floating bars and typically use cables for tension elements and oversized struts for compression elements to give a sense of space. They have been the focus of interest from both engineers and mathematicians from the field of rigidity theory. When considering these structures, typically a stiffness matrix is constructed and a linearised approach is used to determine the deflections of a pre-stress-stable structure when it is subjected to external loads. In this paper, we consider a different approach which allows the large displacement behaviour to be considered. This is essentially a non-linear approach as the stiffness depends on the applied load. It is important to consider this large displacement behaviour as it can lead to softening behaviour or even buckling. Similar to the field of buckling analysis, the key to this paper is to consider the framework in its deformed configuration. In this deformed configuration, there may exist an equilibrium path for the load, whereas in the undeformed geometry there existed no equilibrium path. From this deformed geometry, one can use any statics approach to find the accompanying internal forces and relate them to the pre-stress of the structure. Throughout this presentation, we will use the example of a tensegrity dome, or Geiger dome, similar to the stadium roofs designed by David Geiger. This paper uses graphic statics to find the equilibrium path for the loaded structure. This is because the graphical nature provides additional insight into how the structure behaves and how it can be designed to change this behaviour. Graphic statics is a method which uses the duality between the form diagram, which describes the structural geometry, and the force diagram, which describes the forces within the structure. This will be discussed extensively throughout this conference, so we will move on quickly to its applications in this paper. Consider the tensegrity dome shown with a pre-stress across the long horizontal bar. This bar is in compression to make the framework stable. This bar is also the only extensionable bar in the framework. A loading funicular is added to the framework to apply the external load. One can then change the geometry by activating the mechanism and consider the new force diagram. By doing this in code, one can quickly consider a large range of displacements and plot the load displacement curve. It is useful to normalise the force against the pre-stress in the horizontal bar as the stiffness is proportional to the pre-stress. Different boundary conditions produce different graphs, but they tend to be very similar, as in this example. In this example, for positive P, the structure stiffens, as you may expect. However, for negative P, the structure softens and the displacements are larger than predicted from the linearised analysis. For small displacements, the linearised approach agrees with this method, but they deviate for large applied loads and larger displacements. Some structures can stiffen significantly, such as this one. When the applied load is directly underneath the support, the applied load goes to infinity in the graph. Our paper also discusses an extension to the work of Sergio Pellegrino, who introduced product forces. Our work takes a graphical approach to this. A correction factor was introduced to consider the large displacement behaviour of pre-stress-stable mechanisms. This has shown good agreement with experimental results. Our paper introduces a graphical method for determining this correction factor, but we will not discuss this further in this presentation. There is a lot of scope for future work based on this paper, including future research into the impact of the structural softening and buckling of pre-stress-stable mechanisms. As this class of structure becomes more common, it becomes even more important to understand their behaviour. We hope that you enjoyed this presentation and the accompanying paper. We refer you to the paper for further details. Please also feel free to reach out to us if you have any further questions or would like to discuss possible future collaboration. Thank you for watching this video presentation. We welcome any questions from the virtual audience.